Hey, how's it? This is Austin T. This is Lab 3 Actuators. Okay, we're going to be trying three different circuits today. The first is just the actuator, which will be shown later on. The second is a open loop with the actuator. And the third is a closed loop with the actuator with some added sensors to it.
Alright, so this is the T-boy we're going to dismantle. It's actually meant to drop a tea bag in and pull it out when the timer is finished.
Okay, so this is the penguin opened up. You can see that little black part is a 3D printed mount with the DC motor inside. Okay, this is a close-up of the motor. You can see it's just a small DC toy motor with a threaded shaft. Attached to the shaft is a little black 3D printed part, and that black part connects to the various yellow and white levers of the penguin. And if you look in the background, that pencil is attached to the yellow lever, so that allows the pencil to move up and down by commanding the motor. Okay, so one thing about this penguin design is that it's made out of a lot of plastic that has very loose tolerances. There's no metal bearings or anything like that. So there's a lot of play and sponginess going on. Okay, this shows a little bit better of a view of the inside of the penguin. As you can see, there's a lot of little plastic parts with loose tolerances. There's a return spring over there.
Also, these levers are also a little bit on the spongy side. So the spring may not always give consistent returns over there. That might be an issue of why every time you exert force, it kind of just springs around a little bit.
Okay, this is the first circuit. This is the linear actuator. You got the Arduino on the left, sending the signals to the motor. So through the serial monitor, which you'll see later, the user can enter 1 or 2 or 3 to control the speed of the motor or stop it completely. In the middle of the screen, you see the motor driver powered by the 9-volt battery, and the far right side is the motor itself.
Okay, first test, actuator. So as you see, we have input to the serial monitor. We are going to enter 1 to fast forward this lever right here downwards. So let's do it. And then we are going to enter 3 to stop it. Alright, it stopped. And then let's enter 5 to reverse it. So this lever goes back up. And as you can see, there's no really like feedback for this, so I can try to push down on this. There's no feedback. The motor will try to keep pushing through it. So let's enter 3 to stop. And that concludes test 1.
All right, test 1 results was that the material construction of the penguin is not built for precision. There's too much play with the plastic tolerances, the motor, the spring return. And the second thing is the serial monitor is a very good tool for the user. It allows the user to set the speed of the motor, the direction, and it also provides feedback as well. All right, the next test is the open loop circuit. Same exact electrical circuit, same serial monitor input, except this time we're going to be attaching a rubber band to the lever and we're going to lower the lever down to touch a toy piece.
So we're gonna get this yellow rubber band to come down and touch this little wooden guy. To do that, we will enter number 1 in the serial monitor to lower this little crane. Alright, enter 1. As you can see, there's no way to really get any feedback from the system. It's dependent on the operator to both observe the rubber band and observe the little silver screw over here. So as soon as we touch the conductor with the yellow rubber band, we'll press 3 to stop it. All right, entering 3, no. All right, it stopped. And now we're going to enter 5 for fast reverse. This will bring the crane back up.
Okay, we're going to go fast forward this a little bit, and then we will analyze the results of the open loop circuit. All right, test 2 results show that the system is dependent on the user to start and stop, so the user must be constantly monitoring the system. There's also no feedback on the fully up or down lever positions. So if the user's not paying attention, then the motor will attempt to drive the lever up or down to the max limit until the motor stalls out. There's also a lot of time variation between each full cycle. I believe this is due in part to the material construction and the loose tolerances mentioned in the actuator circuit. On the plus side, the system is very cheap to implement. It's also fairly easy to troubleshoot and understand for everyday users. The code also allows the user to adjust the speed of the motor and see feedback, just like the first circuit. Okay, the last circuit is the closed loop circuit. This was an attempt to make it a fully automated set and play system. So as soon as you start the system, it'll just keep going and going. Okay, so I attached a pencil to the lever this time, and there are 2 sensors in this system. The first sensor shown in the upper portion of the diagram here is just 2 contacts that are separated. So the lever will lower the pencil down, touch the pencil lead between those 2 contacts, complete the circuit, and that will send a signal. And the second sensor is just a NC momentary push button. It's mounted above the actuator. So the lever will lift the pencil and the eraser portion on the pencil will reach up and push in that button.
All right, button got triggered. So it's backing off the button. As you can see, it's a little spongy on detecting that button.
All right, test 3 was a success. The first thing about this closed loop system is that it's a set and forget kind of system. It's a basic automated system that allows a user to pretty much install, press play, and let it run. And then the user just monitors for problems and adjusts. Okay, so next, this system would be well suited for an application with changing external factors. such as various types of objects. However, as seen with the button, the repeatability of the system is not reliable between each lever cycle. This system is not suited for applications that demand repeatability of time between each cycle. And next, surprisingly, the accuracy of the detection was 100% once the mounting was set. The number of backouts varied, but the sensors always ended up triggered in the end. Finally, the repeatability of backouts, as mentioned, was widely varied. This was due to a combination of loose plastic tolerances, non-sturdy mounting solutions, and the mechanical characteristics of the sensors and the graphite. The graphite actually started to get chipped away the more the sensor was used. Alright, right on. Thanks for watching. Special thanks to Banana Robotics for the motor code. Thank you.